Now we're going to look at series interconnections and how that relates to minimality. So here again we have two series interconnections, and here we have these dimensions that we're looking at, M1, M2, and P2. And so this input is of dimension M1, this is of dimension M2, this is of dimension P2. We have the state models A1, B1, C1, D1, A2, B2, C2, D2. Excuse me. And here are the state models written out. And when we combine the state models, so notice that y1 is equal to u2. So when I plug this into here, I get these two equations. And so we get this overall state model with x1 dot, x2 dot, and this state model. So we've seen this before. So the question now is, we assume that the original two systems are minimal. We want to see under what conditions the resulting system is not controllable or not observable. So we have already seen in the previous video an example of a series interconnection where we had cancellations occurring. How does that affect controllability and observability? That's the question. So the hint, pole zero cancellations may occur. So the question is it possible that there is a non-zero vector of this form that could be associated with an uncontrollable mode of the system? Now I've actually, by specifying it of this form, I've actually kind of done a little work ahead of time, but we could go through and assume a full vector v1 and w1 and w2, but we'll start here for now. Okay, so remember, in order to prove uncontrollability, you need to have the left eigenvector of the overall A matrix being an eigenvector, and that same vector multiplying the overall B matrix being equal to 0. So if we multiply this out and set it equal to, so when we multiply this out, we get this stuff. Okay, so it simplifies down to this. And we would need this then to be equal to lambda times this vector, which is given here. And then we would take this vector, multiply by this, and get 0. So when we multiply these two things together, we get this, we get 0. So what is this telling us? So if we were to have a vector of this form, that were an eigenvector of the overall matrix, and a vector of this form that multiplying the overall B matrix giving 0, that would require these two things. That would require, first of all, W1A1 equal to lambda 1 W1. What is that saying? That's saying that W1 is a left eigenvector of A1. W1B1 equals 0. What is that telling us? Well, W1 is a left eigenvector of A1 associated with lambda 1. W1B1 equaling 0 means we have an uncontrollable mode of A1B1. However, our system, A1B1, does not have an uncontrollable mode. It was minimal. Minimal, remember, being controllable and observable. So it's controllable. So therefore, such an eigenvector cannot be of this form. It cannot be of this form. There cannot be an eigenvector of this form that can be used to prove uncontrollability. Okay, so the reason I started with that is to show that we cannot have that. So we now start with a vector of this form where we have a W2 where W2 is not 0. W1 could be 0. W2 cannot be 0. So when I multiply this out, I get all of this stuff. Set it equal to lambda times this, and that gives lambda W1, lambda W2. And notice that when I multiply this times this, I get just W2 times A2. And so this shows that just multiplying this out and setting them equal to each other, I'm going to get a relationship. So if this is equal to, if this quantity is equal to lambda times this vector, that means the W2 is the left eigenvector of A2. It's a left eigenvector of A2. Okay, so that's what this is telling us. So if for any eigenvector of this matrix, left eigenvector of this matrix, the W2 is the left eigenvector of A2. That's what this is telling us. Which is not surprising because this is a block triangular matrix, and so the eigenvalues of the overall matrix are the eigenvalues of the block diagonals. So the eigenvalues of A1, eigenvalues of A2, and so it's not surprising that you would have an eigenvector of this overall matrix that is an eigenvector, that is related to an eigenvector of A2. Okay, so that's one thing that we have. The other thing is that we have this quantity being equal to lambda times W1. But we've seen that W2 can be written as 1 over lambda times this quantity. Or another way of looking at it is by equating these two directly and factoring out W1, I can look at it this way. W1 is equal to lambda I, so that I'm basically taking that W1 times A1 over to this side, and so that's equal to this. Since A2B2 is controllable, so then W2B2 must be non-zero. Why? Well, if W2B2 were 0, this would be 0, and this would be 0, but that would mean that W1 is the left eigenvector of A1. And so this cannot be 0, this cannot be 0, or this would be a left eigenvector of A1, and we've already seen that can't happen. So we're going to assume for now that lambda is not an eigenvalue of A1. That means this determinant is not 0. That means we can solve this equation for W1 this way. And so for lambda to be an uncontrollable mode, when we multiply this out, so notice up to this point we've only been working with the W times the overall A matrix. Now we're going to work with the W times the B matrix. So W times B is this, so it's equal to 0 if this quantity is equal to 0. But we've already seen that WB2 from, so here's WB2. W2B2 cannot be 0. And so we can go through and show that okay, how is this working? WB2 times D1, that's this term, W1B1. So if I multiply this by B1, I'm sorry, on the right by B1, W1B1, then I would have W2B2 is equal to this. Okay, so what is this saying? This is saying W2B2 times this quantity is equal to 0. That comes from this. And so W1B1 is equal to all of this stuff, which is equal to minus W2B2 D1. Okay. So we have those equations, and what the important thing is from all of this is that this must be 0. But if we look at what that is the transfer function of G1 evaluated at lambda. So what this is saying is that G1 has an invariant 0 at lambda. So the conclusion is that the plant 1 has a 0, an invariant 0, at the same frequency that plant 2 has a pole. Okay, did you get all that? Okay, let's go back and look at how that worked. W2 is equal to W2, A2 is equal to lambda W2. So I have an eigenvalue of A2 in all of this. So lambda must be an eigenvalue of A2. Okay, so that means it's a pole of the second system, G2. And what we've gone through and shown is that G1 has an invariant 0 at that same value of S. Okay, what we've gone through and shown is that we have an invariant 0 at that same value of S. So the conclusion, plant 1 has a 0 at the same frequency as plant 2 has a pole, and they cancel. But it's not just that they have a pole and a 0. Remember, we have poles and zeros in multivariable systems, but the 0, remember, and particularly invariant 0, has a direction associated with it. Okay, so it's not just that plant 1 has a 0. It has a 0 with a direction that lines up with the pole direction to bring a cancellation. So there's actually a number of things going on here. It's not only has a pole 0 at the same frequency, but there's a direction that's working. So basically what happens is this connection renders the system uncontrollable, since the mode lambda in block 2 cannot be controlled by U1. Okay, cannot be controlled by U1. So that's important to understand. Okay, so that's the series interconnection. Can we lose controllability? And the answer is yes. We can lose controllability. So the input comes in, it goes through the first system. That first system has a 0 that zeroes out the input, so that when it gets to the second system, it zeroes out something of the input, so that when it gets to the second system, I cannot control the mode of that system. So that's basically what's happening. Likewise, we can show that a series interconnection cannot have an uncontrollable mode of associated with an eigenvector, a right eigenvector of this form, where this is non-zero. Where this is 0, this is non-zero. And we can go through and show that would imply that A2C2 is not observable. The second system is not observable. But we already know the second system is observable. So we can go in this. So we would show this in the same way we showed with the other one. Now, if there is an unobservable mode, so here's the A matrix times a general eigenvector where this is not 0. Multiplying out, I get this, setting it equal to this. We have that A1 is equal to lambda V1. And then this times this must be equal to 0. Okay, and we would go through and show in the same way. So here I have an eigenvector, a pole of the first system, and then I have that this quantity is equal to each other. So notice that here I have A2V2 is equal to lambda times V2, so I can take that over to the other side and solve for V2. And when I do that, so I get this. I can also go through and show that C1 V1, since A1 C1 is not observable, A1 V1 here is an eigenvector eigenvalue relationship. So lambda is an eigenvalue of A1. But we cannot have this equal 0 because the system is observable. Therefore, we can go through and show this quantity. C1 V1 is not 0. We can solve this for V2 and get this expression. Plugging it into this equation here, C2 V2, I get this expression. And so I see that all of this gives me the transfer function of the second system and we have an invariant 0 of that. So once again, in this series interconnection, we get a pole 0 cancellation. The cancellation makes the system observable. So again, we have two systems. We're looking at the overall output, and in the overall output, basically it's unobservable. Notice that because this system over here, the second system, is observable, I can clearly observe all the states of this system from the output. So the thing is, can I observe all the states of the first system, which goes through the second system? Can I observe that? And what happens is, if I can get a pole 0 cancellation occurring here. So if this system has a 0 that cancels with a pole in the other system, then I cannot observe the poles of that first subsystem. So, and again, we not only have that the poles and the zeros must match, but also the directions need to match. So this is what happens for a series interconnection.